Hello my dear friends, welcome to IMS GATE Academy. I am Sourav and I welcome all of you to this live session of the fundamental series which we have started few days ago for the subject industrial engineering. My dear friends, I hope that you are enjoying these fundamental sessions because we are touching very fundamental topics as far as the industrial engineering is concerned, and not only that, I'm trying to correlate few mathematical concepts as well to the industrial engineering, and I'm showing you how they are actually applied when you study in maths and when you study in industrial engineering, right? And today's session is going to be the same. Yes, so for the past 2 days I was discussing about normal distribution. I discussed about normal distribution. I showed you that where it is actually applied. I showed you the two most critical applications of of normal distribution in industrial. First in CPM part, and then in the service level model, in that is in probabilistic model of inventory. And I'm sure that you have understood it if you have gone thoroughly. And today, my dear friends, it is going to be the very important session because I am going to touch the basics of Poisson's distribution, exponential distributions, and how they are actually applied in questions of industrial engineering. That is going to be the agenda of the session. My dear friends, individually you might be knowing these two distributions, individually you might be knowing queuing theory. That is not the concern, but the concern is how sometimes it gets so much confusing that sir, matlab, you will only understand after you watch the session. Before that you won't be able to understand what even the confusion is, right? So my dear friends, without wasting any time, let's start today's session. Fine. My dear friends, if you can see this diagram, I have tried to represent queuing, a simple queuing model. What is there? People are coming, people are forming a queue. These are the servers, people are taking service, and eventually people are leaving. You might have, throughout your life, we have been part of so many queues. And my dear friends, it's very safe to say that queues are inevitable part of our life. Everywhere you go, you will have to face the queue. So can we make queue as zero? Queue means a line. Can we make it as zero? We can make it. Yes, we can make it, but is it feasible? On the the cost benefit ratio should also come into picture. Cost, and if you do the cost analysis, it's not very much feasible, my dear friends. Yes, you can say that sir, over here in place of 3, if we can make 20 servers, 30 servers, there will be no queue. But is it feasible from the company's perspective, from the money perspective? No, my dear friends, the cost of waiting reduces, but the operational cost increases massively. So yes, we have to adjust ourselves with the queues. So why are we studying this chapter, my dear friends? What is the motive behind the chapter? The motive is, my dear friends, to improve the performance, to know about your queuing system. On an average, how many people are there in the system? On an average, how much people have to wait for their service? And so many aspects, my dear friends, which we eventually understand with the help of formulas. There is a formula for length of the queue, there is a formula for length of the system, there is a formula for waiting time as given by Little's law. So many things are there, my dear friends. And although in our gate domain, it's very in a limited portion of queuing theory is there, but in reality there are so many models of queuing theory which we study, right? So basically we study queuing just to know about our queuing system and to improve the performance of the queue. My dear friends, length of the system, length of the queues, and eventually as the chapter progresses, that we study. And even in questions also we get a very basic questions like what is the lambda is given, what is the queue length, what is the system length, all these things are there. But the most important thing is about the two distributions that plays a very important role in the beginning of the chapter. And we are going to start right away. Means I can say in the next 15-20 minutes, my dear friends, you would be reaching the climax of the session. Yes, so much important. I'm going to start with the most important thing only. My dear friends, I would be starting this session with only one statement, and that statement is arrival follows Poisson distribution. From your engineering mathematics as well, from your industrial engineering as well. So let me write it. Just a minute. Arrival follows Poisson's distribution. For example, you are going in a bank. You are arriving at a bank. So bank can say that people are arriving at my place. So your arrival is following a particular distribution, and that is, my dear friends, your Poisson's distribution. Now, what is Poisson's distribution? Let's straight away come to this. So, what is Poisson's distribution? My dear friends, Poisson distribution is given by e to the power minus lambda, lambda to the power n divided by n factorial. My dear friends, this is what it is giving you, my dear friend. This is giving you the probability of x arrivals. Sorry, I have to write here n actually. X equal to n I can write, x equal to n if you write. So, let's write it neatly. Just a minute. Probability of x equal to n arrivals to e to the power minus lambda, lambda to the power n by n factorial. So this is giving you the probability of n arrivals in what? This is giving you the probability of n arrivals in unit time. It is giving you the probability of n arrivals in unit time, right? It is giving you the probability of n arrivals in unit time, my dear friends. Yes, just a minute. Yes, this is so. Good morning, Prakibrat. Good morning, Thiru. Yes, so this is giving you the probability of n arrivals in unit time. Now, my dear friends, I am writing another formula. What is this formula giving? My dear friends, most of you would see this formula for the first time. Why? Because generally in maths, as far as your engineering maths is concerned, we are using this formula, that is n arrivals in unit time, but your time can be anything. So this is giving you the probability of n arrivals in time t. So this is giving you the probability of n arrivals in time t. And it is visible also. Why? Because if you put t is equal to 1, if you put t is equal to 1, you would be reaching this formula. So let me highlight this formula as well. So first and foremost thing, my dear friends, first and foremost thing, that this is giving you the probability of n arrivals. This is also giving you the probability of n arrivals, but here the t is unit. Unit means what? It can be per minute, it can be per hour, it can be per month, per year, whatever. But here the time is not in the unit form. It means it can be 25 minutes, it can be 2 hours, something like that. If you talk about this above formula, here the mean is nothing but your lambda, as you all must be knowing from your basic concepts, and here mean is nothing but lambda into t. The mean is nothing but lambda into t. So this is the things. My dear friends, regarding Poisson distribution, let me tell you that Poisson distribution is helpful as far as your in extremely rare set of events. This is the concept from mathematics that I am telling you, right? Now my dear friends, see one thing, I am going to again write this formula, that probability of x equal to n arrivals in probability of n arrivals in time t. Yes, what is this formula? This formula is probability of n arrivals in time t. Now my dear friends, you will see something beautiful in the next 5 minutes. How? I am going to take you from Poisson distribution to exponential distribution just now. Let's see how. This is giving you the probability of n arrivals in time t. In time t. So, probability of 1 arrival in time t. Yes. Probability of 2 arrival in time t, n equal to 2. Probability of 3 arrival in time t, n equal to 3. Probability of 0 arrival in time t. Probability of x equal to 0 arrival in time t. So put n equal to 0. So it will be e to the power minus lambda t to the power 0, 1. 0 factorial is 1. Sir, 0 arrival in time t. Now my dear friends, try to understand one thing, that in time t, if there is 0 arrival, that means the arrival is, whatever arrival is going to take place, that would be greater than time t. For example, if in the next 6 minutes there is no arrival, I can say that the next arrival would be taking more than 6 minutes. Yes or no? Are you able to understand this concept or not? That I repeat again, that if there is 0 arrival in the next 10 minutes, it means that the next arrival, whatever time it is going to take, it will be more than 10 minutes. So, if there is 0 arrival in time t, so it means that if I'm trying to find out that the time which is taken is greater than t, it means what? That the whatever time is taken for the next customer to come, it will be more than time t, and this is nothing but the same. It is nothing but the same statements only. Yes or no? Yes or no? Are you able to understand this thing or not? Are you able to understand this thing or not? Now my dear friends, if I am trying to find out the probability of time more than t, so can I find that time is taking less than t? That means from 0 to t. What will I do? Suppose I have the expression for time greater than t. So can I find out the probability for time between 0 to t, that means less than t? So yes, I have this value. It will be 1 minus e to the power minus lambda t. Are you able to understand or not? Now, my dear friends, try to see one thing. I'm telling you the concepts of your engineering mathematics, that in your functions, let's say you have the PDF. This is the completely, just to give you a better understanding, I'm telling you that suppose you have a PDF. Let's say the PDF is, that means the probability density function is given as f of x. And if I ask you in continuous distribution functions, if I ask you that find the probability between x1 and x2. So what do? We know that we have to integrate this density function from x1 to x2. Then only we will be able to get the probability. So just see this one and just see this one. So don't you think here also I'm finding the probability that time is between 0 to t, and here also it is giving you the probability for x between x1 to x2, and clearly you can see that it is nothing but the integration of density function. So correlating both the things, what I can say, that whatever this expression I have in my hand, that is nothing but the integration of certain function. I repeat again, that here after comparing these two, this is matching with this. So this must be equal to this. Okay. Number two, this value is nothing but you are getting, whatever you are getting after integrating a certain function. So here also I can say that whatever expression I have in hand, I must have got after integration of certain function. That is why, my dear friends, this is the cumulative function. This is the integrated function. So suppose that if I have to obtain fx over here, if I have to obtain the density function, what would I do? Simply I would put d by dx. Simply I would have differentiated x1, x2, f of x dx, and I would get the density function. Similarly, if I have to get the density function, let's say this is some cumulative function of capital F of t. So if I have to get the density function for small f of t, so I will have to differentiate this with respect to t. I will have to differentiate this with respect to t. And what would we get? We would be getting 0 minus e raised to minus lambda t, and then minus of lambda, and ultimately I would be getting minus gets cancelled, lambda e raised to minus lambda t. My dear friends, what is this? This is nothing but your density function in exponential distribution. What is this? Yes or no? This is nothing but the density function that you use in your exponential distribution. And see, my dear friends, I have started in Poisson's and I have reached your exponential distribution. So this is the bridge that we have taken that connects you from a discrete function to a continuous function. Sounds surprising, but see, this is the thing. So now, my dear friends, now that what can we guess from here? It is not for your, we have to learn this derivation. No, it is just for the fact that these two distributions are correlated. Yes, it is correlated. It means now I am telling the statement. if arrival follows Poisson distribution, then inter-arrival time follows exponential distribution. This is the correlated statement. What was this function? This function was probability of n arrivals in time t. Arrivals. Your discrete function, arrivals will be 1, arrivals will be 2, 3, 4, 0, 10. But it won't be 1.5. Why? Because it's a discrete function. But here, my dear friends, this is the time. It's a continuous function. Your time can be 1 minute, 2 minute, 2.5 minute, 3.5 minute, something like this. So this is the time distribution and this is the arrival distribution. So again I am repeating the statement. If arrival follows Poisson distribution, then inter-arrival time follows exponential distribution, and this, my dear friends, I feel that we should write over here. The most important statement is, if arrival follows Poisson distribution, then inter-arrival time, please mind this word, inter-arrival time follows exponential distribution. So my dear friends, this is the very important statement. Similarly, my dear friends, if I can say that if arrival is following Poisson distribution, so departure will also take place. If you are arriving at a bank, you must be departing from the bank also. So arrival follows Poisson distribution, so departure will also follow Poisson distribution. Inter-arrival time follows exponential distribution, so inter-arrival time follows exponential distribution, so inter-departure time will also follows exponential distribution. And inter-departure time का मतलब क्या हुआ? It means that the bank manager is providing you service at what rate? This is the meaning of inter-departure time. For example, if 20 customers are arriving at a bank in a given hour, so 30 customers must be leaving from the bank in a given hour. So you are arriving at some rate and people are departing at some rate. I hope you are getting it, and let me write this down. Let me write this very important concept. So thank you, Pragyabrat. Thank you very much. So arrival follows Poisson distribution. Departure follows also Poisson distribution. Inter-arrival time follows exponential distribution, and therefore inter-departure time, or it is also known as inter-departure time, or it is also known as service time. It is following your exponential distribution, right? Are you getting this point? Is it clear, my dear friends, this point? Is this point clear, my dear friends? For example, that suppose that this is a server, this is a bank server, and people are coming over here. People are coming over here from at some rate, and after taking the service, people are leaving. ठीक है? So let's say people are arriving at the rate of 20 per hour, and people are departing at the rate of, which I am denoting by mu, at let's say 30 per hour. So I can say that over here, every 3 minutes one person is coming. I can say that every 3 minutes one person is coming. So what is inter-arrival time? Your inter-arrival time is 3 minutes. Yes or no? And here I can say that your inter-departure time, or let me write service time is 2 minutes. Every 2 minutes one person is coming, so 60 minutes में 30 persons. ठीक है? So this is all about. So now my dear friends, the most important statement is arrival follows Poisson distribution, service time follows exponential distribution, and this is the statement that we learn by heart. So you should be very careful that when he is saying that arrival follows Poisson, he means arrival, not inter-arrival time. And when he is saying that service time follows exponential, service follows exponential distribution, so he is saying service time and not departure rate. He is not referring to departure rate. Okay, so no issues. I am so what I am trying to show is that suppose this is a server. So people are arriving over here with some rate. Let's say people are coming at 20 per hour. And after taking the service, people are going. So people are going at the rate of, let's say, 30 per hour. Okay? And this mu must be greater than lambda, then only the system, the entire system will work. So over here, in 60 minutes, 20 persons are coming. So I can say that inter-arrival time means if I have to say that every person is coming in what minutes? Every person coming in 3 minutes. 60 by 20. Yes or no? 60 by 20. 20 persons coming in 60 minutes. One person coming in 60 by 20 minutes. That means 3 minutes. And this is your inter-arrival time. So over here, what is the service time? If in a banking facility, in 60 minutes, 30 persons are leaving. So every person must be leaving in 2 minutes. This is your what? This is your service time. So what do we say? We say that arrival follows Poisson distribution and service time follows exponential distribution, and this is the thing, right? So I hope that I have talked in very detailed way about inter-arrivals time and all these basic concepts. Now the most important thing is, my dear friends, we are very much confused about this lambda. Yes, I know that the biggest confusion over here is what is lambda? Lambda is your same arrival rate, and it is the same lambda that is used in this formula and it is used in this formula. Yes, my dear friends, let me repeat it very clearly that many students have doubt that sir, this lambda is different or same than this lambda, because if you recall your engineering mathematics concept, there also in Poisson lambda comes and in exponential also lambda comes, but you never think about this that sir, both the lambdas are same or not. Yes, my dear friends, let me tell you very clearly that this lambda is also same, this lambda is also same. Point number 1. Point number 2, sir, when we will use this formula and when we will use this formula. So whenever he is asking the probability of certain arrival which can be in numbers, natural numbers, so obviously we will be using Poisson's formula. And whenever he is asking something about time, that your what is the probability that the time spent will be less than 5 minutes, 6 minutes, whatever time related thing he will ask, I will use this formula. Clear? This is clear or not? Okay. Arrival, time, lambda, same. But here is some hack, my dear friends. There is some trick over here. Let me tell you what. My dear friends, this is the what is the exponential function? The exponential function is lambda e to the power minus lambda t. So if say lambda is given as 20 per hour, 20 per hour, and he's saying, let's say he's saying something, he's asking something related to time, that what is the time, that it is 1 to 3 minutes. I'm not framing a question, but I'm just giving you an example that suppose lambda is given in 20 per hour. So he's asking you something, anything he can ask you. I'm not framing a real life question. I'm just giving you that what we should do over here. So whenever he's asking you probability, so you will integrate it and you will write lambda e to the power minus lambda t, and it is 1, 2, 3. Now the question is, what should we put over here? The question is what we should put over here. Should we put 20? Should we put 20? My dear friends, let me tell you, you will not put 20 over here. Now you will tell me that, sir, just now you told that these two formulas are same. These two formulas are same. These two formulas are same. Okay, just a minute. He has given you lambda equal to 20 per hour, and he is asking you what is the probability of 2 arrivals in a given hour. Let's say he has given this data and he is asking you the probability of, let me erase everything and then explain you neatly. He has given you, just a minute. He has given you lambda is equal to 20 per hour, and he is asking you what is the probability of 2 arrivals in a given hour. 2 arrivals in a given hour. So you know, my dear friends, whenever unit time is concerned, unit time, so we use what? E to the power minus lambda, lambda to the power 2, because 2 divided by 2 factorial. So what value of lambda you will substitute? You will substitute lambda is equal to 20, and that is very much e to the power minus 20, 20 to the power square by 2 factorial, and you will get your answer. Suppose that related to time, he asks that t is between 1 to 3 minutes. 1 to 3 minutes. 1 to 3 minutes. So you will use this formula. You will definitely use this formula because he is asking in minutes. So what you will do? You will do lambda e to the power minus lambda t and 1 to 3 minutes. And now when you substitute, the question is, will you substitute 20 over here? Will you substitute 20 over here? No, my dear friends, you will not substitute 20 over here. Sir, why? It is because you are dealing in minutes and you are putting, the examiner is asking question in minutes and you are putting lambda as 20 per hour. How it is possible, my dear friends? How it is possible? How it is possible, my dear friends? You are dealing in minutes and you are putting things in hour. How it is possible? That is why you have to substitute lambda in terms of minutes. And how will you convert? You will convert in this way, that lambda equal to 20 per hour. So 60 minutes में 20 people are coming. So 1 minute में 1 into 20 by 60, 1 by 3%. And this equal to lambda is equal to 1 by 3, which you will be substituting over here. Is it clear or not, my dear friends? Is it clear or not? Very, very, very important concept, my dear friends, that we are discussing over here. And I'm sure that if you understand this, there will be no confusion as far as your Poisson and exponential distributions are concerned. Is it clear, my dear friends? Is it clear? Tell me. Is it clear, my dear friends? Okay, and no matter how much theory I explain you, it won't be very much clear until and unless I show you a problem. So it's time to do a problem. My dear friends, this is not a random question. This is a question from GATE 2018. Please read the question, my dear friends. Please read the question. Please read the question. Thank you, Pragya. Thanks a lot. The question is saying the arrival of customers over fixed time intervals in a bank follow Poisson distribution. Now you know very clearly, with an average of 30 customers per hour. 30 customers per hour. The probability that the time, now see, here is the thing. The time between successive customer arrival is between 1 to 3 minutes. So my dear friends, he is asking what? Is he asking about the arrival probability or is he asking about the time probability? Clearly he is asking about the time, the probability that the time. So time follows what? Time follows exponential distribution, not Poisson, exponential. So now I know that the density function is going to be my lambda e to the power minus lambda t. And whenever he is asking you about the probability, so you know that it can only be obtained by integrating the density function. So this is the density function, my dear friends, and it will be, if I want to know the probability, let's say between 1 to 3 minutes, na? So 1 to 3, so I will get only by integrating lambda e to the power minus lambda t, and it is between 1 to 3. ठीक है? Yes, so let me integrate it, my dear friends. Let me integrate it. Probability for the event will be getting lambda e to the power minus lambda t divided by minus lambda. It is between 1 minute to 3 minutes. It is minus e to the power minus lambda 1 minute to 3 minutes minus 3 lambda, I am substituting 3, plus e to the power minus 1 lambda, and you are left with e to the power minus lambda minus e to the power minus 3 lambda. I hope the mathematical things are clear till now. Now the biggest question over here is, what should we put over here? What should we put lambda? Should we put lambda equal to 30 customers per hour? Just now, my dear friends, just now only I have told you that how can you substitute lambda equal to in hour when you are dealing in minutes? You have substituted 1 minute and 3 minutes over here. How can minute and hour coexist together? That is why this needs to be not per hour but per minute, my dear friends. So if now in an hour 30 customers are coming, it means in 60 minutes 30 customers are coming. So 1 minute mein 30 by 60, that is 0.5. So 0.5 customers per minute. And my dear friends, when you recognize this, you can very easily substitute over here. So let me take it next page. The probability was e to the power minus lambda minus e to the power minus 3 lambda, and therefore you will substitute lambda is equal to 0.5. So e to the power minus 0.5 minus e to the power minus 3 into 0.5 is 1.5. My dear friends, you can solve this by using your calculator. That is not the important. Right? So please definitely solve it and you can drop your answer in the comment section, right? My dear friends, I have many such questions with me which will clear your doubt, and this is another type of question, my dear friends, and in this question also I will explain you one very interesting concept related to exponential distribution. ठीक है, just read the question. Just read the question. Calls arrive on an average of 12 per hour. Find the probability that a call will occur in the next 5 minutes. My dear friends, whenever you when you see minutes, you would know that, sir, this should not be in per hour, this should be in per minute. And immediately, the first thing you will write is that 60 minutes mein, if 12 calls are coming, so 1 minute mein 12 by 60, 1 by 5. One by 5 calls will come. Okay, so this will do. Now, calls will occur in the next 5 minutes given that you have already waited 10 minutes for a call. I request you to read this question again. Find the probability that a call will occur in the next 5 minutes given that you have already waited 10 minutes. Means 10 minutes you have waited, and now he is saying that, sir, call will occur. What is the probability that call will occur in the next 5 minutes? So if I start taking time from 0, so it means he is saying what? See, he is a good examiner. He has already given you what he is trying to ask you. He has given a condition. You can also refer this as a question of conditional probability. And he has given you a condition that t should be less than 15 minutes given that already 10 minutes have elapsed. Now, my dear friends, let me tell you another interesting concept. This is the forgetfulness nature of exponential distribution. I repeat again, forgetfulness nature. In Hindi, forgetting something, bhool jana, forgetting. It means that the nature of exponential distribution is in such a way that whatever has happened till now or whatever has happened in the past, the probability for the something upcoming is not dependent on it. Yes, it does not take into account whatever has happened. Whatever is yet to come, it will take into account. It means that already if I have waited 10 minutes for the call, it does not matter. What matters is the next 5 minutes. It means that this thing can be written as, 10 minutes have already elapsed. And he is asking in the next 5 minutes. मतलब 15 minutes से 10 minutes minus करो 5 minutes. So he is in a simple language, he is trying to ask you t less than 5. It means he is asking you time is from 0 to 5. My dear friends, you have the lambda value. अच्छा, he is asking about time. तो टाइम के लिए विच डिस्ट्रीब्यूशन विल यू यूज? एक्सपोनेंशियल. ठीक है, यू विल यूज एक्सपोनेंशियल. सो बिटवीन 1 to 5, 0 to 5. So clearly the probability is integration lambda e to the power minus lambda t 0 to 5. So if you just do the integration, you will come at this, and where t is nothing but 5. So 1 minus e to the power minus lambda. What is lambda? Lambda is 1 by 5. 1 by 5 and t is 5. This cancels out, and 1 minus e to the power minus 1. 1 minus 1 by e, and you can solve this to get the answer. Right. My dear friends, similarly, many questions you will get. Many questions you will get based on this. So here also you can see if jobs arrive at every 15 seconds, that is lambda is 4 per minute, what is the probability of waiting less than or equal to 30 seconds, that is 5 minutes. So see, if you want to use lambda equal to 4 per minute, if you want to use this number 4, you better, don't use it in seconds, you can use it in minutes only. Yes or no? See, it's all about the time consistency. Minutes, hours, seconds. Okay? So less than 5 minutes means he is asking 0 to 5 lambda e to the power minus lambda t dt. So see, I'm not writing dt in every integration, it's an understood thing, that is not the important thing. So what you will do, you will substitute lambda directly equal to how much? 4 per minute, and everything is same, you will get the answer. So you can do the calculation and drop the answer in the comment section. I will check it personally. Now my dear friends, let us do a till now whatever questions we have discussed, it is time. Now by saying this, I have already given the hint that this question is going to use which distribution. Please read the question, my dear friends. Please read the question. Please read the question, my dear friends. So the question says, in a bank, customers arrive at the rate of 20 per hour as per Poisson distribution. The probability of 4 arrivals in a span of 6 minutes in any given hour is what? My dear friends, if you solve this question of Poisson, very simple question, it's a simple question, I'm not saying it's a very difficult question, but if you solve this question of Poisson, you will be in a very good position conceptually. He's saying that, first of all, he's asking you the probability of 4 arrival in a span of 6 minutes. N arrival in time t. Yes or no? N arrival in time t. So till now we know that what is the probability for x arrival. So it is e to the power minus lambda to the power x by x factorial. But this is what? This is the probability of x arrival in unit time, not any time t. So whenever, so let me solve it in terms of n only. E to the power minus lambda to the power n by n factorial. So this is n arrival in unit time. But whenever he say that n arrival in time t, so what you have to do, I have already discussed, e to the power minus lambda t to the power n by n factorial. Yes, very good, very good. So 4 arrivals he is asking, so it is not very difficult thing to point out that n is equal to 4. But what about lambda and t? What about lambda and t? So let's say if you put t in as a span of 6 minutes, so can you substitute lambda is equal to 20 per hour? Does your common sense allows you to substitute lambda equal to 20 per hour? How can hour and minute coexist together? So my dear friends, you have already understood it, that it should not be in terms of per hour, it should be in terms of per minute. What I want to say, that if in an hour, that means 60 minutes mein, if there is 20 arrival, so 1 minute mein there will be 20 by 60, 1 by 3 arrival per minute. And now my dear friends, lambda is equal to, lambda into t is what? 1 by 3 into 6, and that is 2. So lambda t, that complete lambda t value is 2, and now happily you can substitute over here. The probability of x equal to 4 arrivals is e to the power minus lambda t to the power 4 by 4 factorial, and lambda t value is 2, so e to the power minus 2 to the power 4 by 4 factorial. If you solve this, you will get the answer. So my dear friends, this was all about the complete correlation. I have not taught you exclusively Poisson. I have not taught you exclusively exponential. I have not taught you even queuing theory. But this was the correlation between all the 3 topics, my dear friends. My dear friends, I request you to please watch this session if needed twice or thrice, because this is going to clear some major, and I will not say major, I will say very minor, basic concepts as far as these distributions are concerned and their role in queuing theory. My dear friends, if you understand this, the latter part of this chapter, you will not face any problem, because now the formula will be all on simple, very basic calculations. Again, I will just give you a hint that you will say expected length of the system, expected length of the queue. All these formulas will come into picture. And just notice the word expected. Expected means what? Expectation. Expectation where it is used? In probability. So by using the formula for expectation, you will reach this formula. So just see, my dear friends, that how probability is there in your entire queuing theory. How probability is there in your entire PERT, CPM PERT, normal distribution, and how normal distribution is there in your entire inventory probabilistic model, service level model. So my dear friends, I hope that you have enjoyed this session, and if you are finding it useful, please share it with your friends. They can benefit from it. If you have any doubt, you can leave comment at this video section and comment section, and I will personally reply it. I will make sure that. So my dear friends, I hope your studies are going well. Work hard. GATE is not very much far from now, and we will help you as much as possible. For any case, you can contact us, and I wish you all the best. Do like and share. Till then, stay tuned. God bless. Thank you, my dear friends.